So this is I changed the topic actually yesterday because I gave a talk on the title on the schedule last March in IHP, and I see that many people were there. There's significant overlap. So I might want to talk about something else today. So this is a joint work with Michael de la Salle, Nicolas, and Michele. So it's about something called critical regularity of a group. So I'd like to give, first of all, a kind of overview talk about the subject, critical regularity of a group. So critical regularity is rather a concept or propaganda that given a group action, you want to find the best possible regularity without changing its algebra or even topological conjugacy. So a motivating question is the following. Say, suppose you have consider the infinite direct sum of infinite cyclic group. So it naturally acts on itself. Right? You might want to call this as a left regular or lexicographic order preserving. Right? There's very natural action, you just add it, right? And then the question is, does it extend to a smooth action of the form Z into, say faithfully, into diff1 of the interval? So actually, this is the question that we started with. So I'd like to talk about some of the related results and actually more overview about the subject. Or maybe at the end of the talk, you might come up with a better, shorter proof. Because you can easily embed this group into the interval, even as a dense subset. So lexicographic order gives you topological action, C0 action, and you want to smooth it to C1, and I'll talk about why higher regularity will never be possible.
Sorry, do you mind explaining your motivating example?
Oh yeah, so you have infinite direct sum of infinite cyclic group. So that's like direct sum. So it's just finitely many coordinates among the infinitely many possible coordinates, and then it acts on itself by regular action, right? By adding it.
By itself?
Yeah, you just add it. So given a vector and you have a group element, you just u dot v is u plus v. Right? And it comes with natural lexicographic order, right? Because it's finitely many sum of vectors. So there's a natural lexicographic order. So you can embed this countable set into the interval. And if you want, you can just even make it dense. Therefore, it acts on some countable subset of the interval.
Sorry, if those groups are cyclic, how could they have a left order? Z, EI, are they...
Z are infinite cyclic groups. Sorry, EI is a vector, name of a vector. Standard basis vector, not the number.
Okay.
Sorry.
So right-hand side is the same.
Same group, yeah, same group, yeah. I was lazy not to write down the name of the basis. So it has topological action on the interval, and the question is, can you make it C1 or even higher? Okay. So this kind of question is dealt with in terms of critical regularity. So let's say M is a manifold, say compact, connected, and mostly one manifold. Almost all the time I'll just talk about one manifold, although maybe once or twice I'll talk about some higher dimensional action. And if, say, R is a real number, then this group kind of appeared implicitly in this weak as well. So you can talk about the collection of CR diffeomorphism group of M, right? So you can just collect all the, say R is written as its integer part k plus tau. K is the integer part. Then you can talk about, say, G is ck diffeo. That means ck map, and the derivative is non-singular. And its kth derivative is locally tau continuous, but because I'm talking about tau Helder continuous, tau Helder. Because I'm talking about compact manifold, so locally it's not necessary. But if you want to talk about non-compact manifold, you should put local Helder continuity, because global Helder continuity is just too strong.
Excuse me, I'd like to understand notation. When you write the sum of infinitely many summas, it means my infinite sequence is only finitely many.
Infinite sequence, but finitely non-zero.
Only finitely many.
Yes, that's correct. Yeah. Yes, it's not infinite direct product. Right, and then, so you can talk about, so given a group, so say the theme or meta question is given an action from a group, let's consider faithful action, it doesn't really matter, of the homeomorphism. We want to find the best possible regularity. So the first question is for which R is row topologically conjugate into diff R. Which is the question. And second question is for which R does there exist row prime? So we only care about the algebraic structure into diff R. So in some papers, one calls number 1 as topological smoothing, number 2 as algebraic smoothing. So for number 2, you only remember the algebraic structure, and you want to embed it into CR diffeomorphism group of the interval. Okay, so from this we can introduce a definition. So maybe I'll just keep the definition here. So given a group, say you can define critical regularity. So it's an abbreviation for critical regularity. With respect to M of a group is the largest possible such number, such that G embeds into diff R of M, with understanding that supremum of empty set, well, it depends on which set theory textbook you use. It's, I guess, negative infinity. So if you cannot embed into any diffeomorphism group, it's considered to be negative infinity. But other than that, you can also there's, but this is, even if you compute critical regularity, you also have a question remaining. Is it realizable? So does it really embed into that CR diffeomorphism group, or it embeds into any epsilon smaller regularity, but not it to itself? So those are the questions that I'd like to talk about today, or I'd like to overview. Most of the results are not due to me. So let me give you some of the, actually, I can never be comprehensive on this matter, but some of the results that are known. So let me give you maybe one or two examples in topological smoothing, namely question number 1. So Jenny Harrison in 1975, I think that for all manifolds, let's say compact connected, d-dimensional, but d-dimensional, and for all real number R, there exists a representation of infinite cyclic group. That means just single element inside diff R. That is not C0 conjugate to CS for all SR. So there exists a single diffeomorphism. Of course, it cannot be one because everything is smoothable for a single element. So D is not one. So two manifolds or higher, you can find a single diffeomorphism, which is CR smooth, but you can never smooth it to CR plus epsilon. So she excluded 4 manifolds at her time of writing, but then in 82, Friedman and Quinn, they solved some important important theorem in 4 manifold theorem that Harrison needed. So now 4 manifold is also fine. And Tsuboi, Takashi around 89, and around the same time, Cantwell and Conlon. So they constructed the phenomenon in 1 manifold. So they proved that for all k, actually they considered integer regularity only, but it works for general regularity. There exists a representation rho k from the Lamplighter group that was introduced in Nicholas' talk in the morning into diff k of interval that is not C0 conjugate into higher regularity. So constructed a very concrete map and then gives an obstruction for CK plus 1 regularity. So using fixed points. So having lots of fixed points, and then basically these combinatorics, these fixed points will just too many fixed points on an interval prohibits that the map is conjugate to CK plus 1. And of course, many other results. But so one of the results that foliation theorists were interested in this topological smoothing is, for instance, in Takashi and Cantel-Conlon result, they were able to deduce that, say, for all k and for all g, there exists a codimension 1 CK foliation, so CK in the transverse direction on SG cross I, not isomorphic to any CK plus 1 foliations. That is not smoothable to say K plus 1 foliation. And the way that they did it is naturally this surface group surjects onto free group, surjects onto 2 free group, and then this Lamplighter group. And then they were able to use diff k of I, and then using this composition as the holonomy map, so to make a suspension of I cross SG, and therefore the resulting foliation. So that is quotient of SG cross I by this suspension. So on the so then you suspend it. So that is, what is suspension? You consider universal cover of I, and then there is a group action of the group action given by this composition of actions. So on the right, it is interval action. On the left, it is deck transformation action. So it gives natural foliation. And this non-smoothability is isomorphic to as a bundle. It cannot be CK plus 1 foliation. Okay. And then there are many other stories, but let me be brief and then just move on to algebraic smoothing, which I'd like to focus on today. So I planned the overview talk on critical regularity, but try not to spend not too much time on it. So for algebraic smoothing, so Thurston, in his famous Thurston stability paper, established that, gave an example that this 237 cipher fiber space, so that can be perceived as the 237 triangle Fuchsian group, and you lift it to the universal cover. So then you get a cipher fiber space of 237 type. So consider, just if you do not know what cipher fiber space is, it doesn't really matter. It's just fiber product of this diagram. And this PSL2R tilde naturally embeds into homeomorphism group interval, or homeomorphism group real line. And then he proved that by his so-called Thurston stability lemma, 237 can never embed into if 1 of I. And because the lemma that he established, which is really has beautiful impact, is that every non-trivial, finitely generated subgroup of if 1 of interval surject onto Z, while the cipher fiber space fundamental group is easy to be seen as perfect. So it can never surject onto Z. So it's just, because this is sometimes called Thurston stability lemma by some people. And this lemma immediately implies that it can never embed into diff 1. So in this case, you can compute the critical regularity precisely, because it's a result due to Deruan, Clepsin, so Victor and Andres proves that every countable subgroup inside homeo of compact connected one manifolds, in other words, circle or interval, is C0 conjugate into, I would say, by Lipschitz, or, yeah, by Lipschitz homeomorphism group of 1. Let's just put +4 to emphasize orientation preserving, although it doesn't really play a role. So here, diff Lipschitz means not differentiable, but by Lipschitz homeomorphism group of M, where M1 denotes one manifolds, I or S1. So in other words, you can embed this, say, cipher fiber space 237 group into, say, diff of 0.5. So 0.5 Hölder continuous, 0.7, 0.9, 0.999, and so forth. Although they are not groups, it doesn't really matter. So critical regularity of, say, interval, compact interval of this group turns out to be 1, but not realizable. So they can embed into diff 0.99, 0.999, and so forth, but not diff 1. And I can just go on forever, even combining the names of the people who are sitting here regarding critical regularity. So for instance, the Christian and Yashloda and Triestino in around 19, I think they gave also example of certain piecewise projective certain subgroup. Actually, it's about the whole group, of course, but certain finitely represented subgroup of piecewise PSL2R subgroup doesn't embed into if one, although it embeds into homeo of I. So this was actually defined by Nicola. So there are more examples now. Actually, there are a lot more examples of critical regularity 1. And in this case, it is not realizable. And actually, my encounter with critical regularity, so there are,
So is the point that Thurston theorem doesn't apply here?
Eventually, they used the Thurston stability theorem, but not directly. So is it right, Christian? You use the idea of Thurston stability kind of, but not as just corollary. Yeah. Okay. Yeah, I guess this estimate that you use for Thurston stability was relevant.
Yes, well, we used a version, it was in my thesis, it's not exactly the same.
Right. Yeah. And also, Andres gave an example of this critical regularity 1 finitely generated group, which is solvable, and it has really nothing to do with Thurston stability. Yeah. And so it's like a kind of research problem generator. You just take your favorite group, favorite orderable group, and try to find its critical regularity. If the answer is too easy or too hard, it's not a good research problem. If the problem is reasonably hard and has some rich structure in its solution, it could be a good research problem. So and then yes, we studied some exponentially growing groups first. So we proved that for all finite index subgroup of mapping class group, so H never embeds into diff2 or any danger class, which was defined in Andres talk. So interval or circle. And the reasoning behind it is that actually we use right-angled arcing groups. So it is actually does a bit strengthened later. That during the pandemic time, so whenever you have a finite index subgroup, say the critical regularity of compact connected manifolds of such a group is always 1. So 1 plus epsilon is never possible. So you can never have 1.1 action. And let me give some idea behind this. But it's also very, I guess, quite influential open question whether is 1 realizable, is C1 realizable for such a group, for such a finite index or mapping class group, because it's related to other important conjectures regarding finite index over mapping class groups, so-called Ivanov conjecture or property T.
So does the surface R have boundaries or functions?
It doesn't really matter actually. So good point. Thanks. Yeah, there's a. I'll mention that. Yeah. So it's also. So actually, it can be any surface, any hyperbolic surface such that 3G 3g minus 3 plus boundary point is at least 3. So then you might wonder, what about the complexity 2? You still have hyperbolic surface with complexity 2, such as twice punctual torus. And that we do not know. That's because actually this is proved by the fact that actually the actual theorem for us is that free group cross free group star Z never embeds into diff 1 plus epsilon of compact connected one manifolds for all epsilon positive. Okay, or even none. You can even generalize the non-solvable cross non-solvable star Z. And this group always persists in any finite index subgroup. Any finite index subgroup of mapping class group of G at least 2. But for the complexity 2, it is not true. So actually the question that we do not know yet is so say for example F2 cross Z star Z. So does it have some C1 plus epsilon action? So this is if this is never possible, then this is related to this twice punctual torus or complexity 2 case. Because you can easily find such a group in twice punctual torus mapping class group. Yeah.
Your theorem does not embed.
Does not. Thanks. Thanks. Right. Never embed. Right. Yeah. So actually, it is a question on so-called right-angled arcing group in disguise. So right-angled arcing group, certain right-angled arcing group can never embed into diff 1 plus epsilon. And with Harry, we proved that it can never embed into Denjoa class, but actually we can improve it to 1 plus epsilon using an idea of Andres that I'll talk about later. Okay. So that's roughly extremely biased quick overview of critical regularity. But let me move on to groups of subexponential growth. So now part 2. And eventually want to come back to the original question that I posed. Oh, right. One more thing that we repeatedly used and might be worth noting is the following lemma, which you might, hopefully some of you might find it entertaining. So we repeatedly use the extremely simple statement, which wasn't completely trivial for us. So the lemma that we repeatedly used, we call it as ABT lemma. So you take 3 C1 diffeomorphism of the interval and say support, namely the complement of the fixed point set and support of B are disjoint. So in particular, they generate abelian group. Then necessarily, those 3 generator group, generically, they might look like Z. You might think that it should look like Z2 star Z, but the theorem is it can never be isomorphic. So that's the ABT lemma that we repeatedly used. So whatever T you choose, whatever generic T you choose, or it doesn't have to be generic, whatever special T you choose, there is always a hidden relation coming from this disjointness of the support. And then that's what we repeatedly exploit in C1 topology. And then C1 plus epsilon, we need some distortion argument, so-called. Okay. And then there is also huge literature on the critical regularity of groups of sub-exponential growth, especially from southern hemisphere. So, say part 2.
But maybe before you continue, does F2 cross Z embed into this?
F2 cross Z. So algebraically, you can easily embed it. You just take between 0 and half, F2 is acting, and half and 1, Z is acting. Right. Or even you can make it overlapping, but it's, so you have to cross Z is easy. Yep. But if you just make it F2 and Z and their supports are disjoint, then ABT lemma will tell you that you can never succeed. The free product, the image of free product will never be free product. That's the content of ABT lemma. Yeah, so yeah, that's the whole point. Thanks. So what does it have to do with the sub-exponential growth? So a result due to Favre and Frank's, it was published in 03, and it was strengthened and corrected. So there is some minor error in Favre-Frank's paper, but Whittaker found it and revised it, and then I think they put a revision in 2021. So Whittaker around 12. And also, yeah. So they proved that every finitely generated torsion-free nilpotent group embeds into if one of the compact interval, and they were even able to do a residually torsion-free nilpotent group so that it contains many other braid groups or right angle arcing groups and so forth. And actually the regularity, so for nilpotent group, actually they can embed in, right. So what they actually proved is this universal nilpotent group, that is ones on the diagonal and integers on the upper right part. So if it is known that every finitely generated torsion-free nilpotent group embeds into here, and then what they did is they embed into C1 Diffeomorphism group interval. And of course, there's also, yeah, maybe I should have mentioned Gis and Sergisque, especially because we were in France, that Thompson's group F embeds into C infinity Diffeomorphism group interval, but it was seen before in one of the talks by Andres. Right, and then there are several developments in this matter. So Whittaker, Navas, and Rivas in 2014, they and before, yeah, now I'm becoming obscure about the years, but Castro and Navas and Rivas around, yeah, correct me if I'm wrong, but something like, they started to compute the critical regularity of the nilpotent groups. Yeah, 14 and 18. Yep. So they proved that critical regularity of actually interval or circle doesn't really matter. Let's compute for the interval of this 3×3 step 2 nilpotent group. So Heisenberg group. Integral Heisenberg group is 2. So not realizable. So not realizable was known before, but they proved that 1.9 or 1.9 or 1.99, and they're all possible. And they also consider this 4×4 universal nilpotent group. So this critical regularity is 1.5. And Maxi this morning told me that with Victor, they can prove that it is not realizable. Is it right? Is it right? Yeah. Yes, I heard of this morning, that not realizable. Even in a more general step, many bigger sized step 2 nilpotent groups, they are able to compute. They are able to prove that critical regularity can be computed and cannot be realized. It will never be realized. And probably there are other nilpotent groups that I'm missing, but I'm slowly moving to the group of sub-exponential growth. So what about the intermediate growth groups? So we talked about exponential growth groups, some of the exponential growth groups and polynomial growth groups. So what about the sub-exponential growth, the intermediate growth group? And Andres proved that if, say, let's talk about two things. If, say, G is group of finitely generated intermediate growth, that means it is strictly sub-exponential, strictly super polynomial. Then it can never embed into if 1 plus epsilon of the interval. So even if it is orderable, it may be by Lipschitz, but also he gave an example, so-called Grigor-Chong-Maki group. Key group. So the precise definition doesn't really matter today, but it is, I'll just say, it is some 4-generator group, subgroup of infinite automorphism group, infinite valence tree. And this is the intermediate growth. So it can never be C1 plus epsilon algebraically smoothable, but this group embeds into, so he gave a concrete embedding of this group, if C1 Diffeomorphism group interval. And how Andres used intermediate growth. So, well, one of the ideas, of course, there are many, many steps, but one of the ideas is that if you have a intermediate growth, let's say sub-exponential growth, and C1 plus epsilon, then you will never see the crossing of the support. So this will never appear in the picture for group elements A and B, because once you see this, then you can apply so-called a ping lemma. You can find a free semigroup of rank 2. Basically, you put a point somewhere in the middle, and you take a high power of A and high power of B, then it will never come back to the original point. So it gives you exponential growth. So you can never see this. So actually there is so-called the level structure. Any two diffeomorphisms in the group, if it is C1 plus epsilon, will either have one of the supporting intervals should be contained in the other. So you have a certain level structure. And you cannot go forever. So, and it's finite level by this distortion argument. If it goes to infinitely many levels, then this epsilon Hölder continuity will produce a contradiction. And then using this picture, actually this key idea of our ABT lemma as well. Some iterated commutators. Iterated commutators. You can have good control on iterated commutators. Iterated commutators, certain whenever you have any two elements or several elements, you iterate the commutating, then it will be trivial using this level structure. So that's the definition of nilpotency. So polynomial growth. So this is the idea we actually repeatedly use. So if you have a subexponential growth and C1 plus epsilon, then you will have no crossing of the supporting intervals. So some people call this as Conradian action. And then using this extra regularity, you find iterated commutators will become 0. So it's just like in the ABT lemma, we proved the same thing. And then for Grigor-Chong-Maki group, so what he used is, so of course, this group by design is orderable, so it acts by C0 on the interval. But you do not know if you make a just random C0 action, you do not know the regularity, so you consider a so-called blow up of a countable orbit and make it smoother. And this idea was used many times in the literature from Denjoa or Pixton and Takashi too. So let me briefly, so yeah, again, I was just trying to give the key idea of the part 2 is using semi-conjugacy or blow up. So blow up is a more natural, I guess, phrase for this description, although it's a dangerous phrase to use in airport or metro, especially if you want to blow up the plane or a line. So it's, we say, suppose you have rho hat and rho 2 representations into homeo of M, say mostly one manifolds. So rho hat is, the definition is completely general. It is just, if you look at any textbook on dynamical systems, you will see for any manifolds, semi-conjugate to rho, or especially in one manifold, it is more naturally is a blow up of rho. If there exists a continuous, surjective, and monotone. You can express monotone, especially in the circle, by the condition that H inverse of a point is connected. So you don't want to wind up the circle twice, such that, so you have a commutative diagram of rho hat G and rho G of the surjections for rho G. So this is not a equivalence relation because rho hat is kind of in the above and surject onto the action of rho, but you can make it make the semi-conjugacy action as equivalence relation by declaring that two representations are equivalent if and only if they have the common blow up. So having a common blow up gives you equivalence relation too among the actions. And guess it was at the end survey article that the semi-conjugacy captures the dynamic property of the action. So anyway, and this blow up was used many times in the literature to smooth a group action. So it was used by Denjoa and strengthened by Ehrman I really don't know the years. Maybe I should know, but 1920s or 30s, and then Ehrman later. That so you have for all irrational rotation number, there exists f in diff, and of course any epsilon near from 2. So diff 2 minus epsilon of the circle, such that rotation number is R and not minimal. So it's not really a rotation. Rather, you take a irrational rotation, pick a countable orbit, and then you blow up. So each blow up to intervals and giving suitable transition functions for the intervals, so-called wandering intervals. We can make it smoother and smoother up to 2 minus epsilon. And then, it can be also, but you can never succeed it in C2 or 1 plus bounded variation, as it appears several times in, say LNS talk. And so actually, it is interesting open question, what is the best possible regularities? You can also show that whenever you have a modulus of continuity, modulus of continuity is a function, modulus of continuity, such that it is not too small. So 1 over alpha x 0, 1 is finite. Then there exists such danger counterexample in C1 comma alpha. So C1, whose first derivative is alpha continuous. So this is one of the example. And it is very interesting open question whether this is necessary. But I guess nobody knows it yet. So is there any danger counterexample of better regularity, better continuous modulus of continuity? Okay, so then now the idea is this blowing up intervals often gives you smoother actions. So right. So what about abelian groups? So let's come back to the Z, direct sum of Z, or even Z free abelian groups. So it is due to Takashi proved, I think, in 95 that there exists this lexicographic order, let me abbreviate, lexicographic order preserving action of Z to the D into if 1 plus, I guess, 1 over D minus 1 minus epsilon. I think this is correct. Yep. So for all D. So, and the idea was exactly the same. So he used, and then, he used the pick a countable orbit and blow up. But what was very important to us, find a very nicely chosen transition map between the intervals. And then it becomes smoother and smoother, and you can reach. So for all epsilon positive, so you can get as close as to 1 plus 1 over D minus 1. And so it is optimal also. This number is optimal. So 1 plus 1 over D minus 1 plus epsilon is not possible. It is also by aforementioned of Deroin, Victor, and Andres. And I guess, so 1C, 1 plus D minus 1 plus epsilon is not possible. And I guess, it's not known whether this number is realizable. So this gives us the corollary that this infinite direct sum of Z, this is direct limit of Z to the D. So we will never succeed in C1 plus epsilon in our original question. So that answers some part of our question. And now the remaining question is C1 possible? So because of this optimality result, so note that there does not exist this, especially these countable groups were not so much considered before. So this countable direct sum of Z will never embed into the 1 plus epsilon of I in the lexicographic order preserving way. Right. Of course, the embedding itself is possible. You just take some flow and then just choose the time parameter as rationally independent numbers, root 2, root 3, root 5, and so forth. And then they will generate a abelian group of whatever rank you want. But in the lexicographic order preserving way, you cannot do that. So basically, we are looking for some blow up of the intervals, but you have countably many generators. So what should we do? And actually, we succeeded, and we found some length assignments for each element. But what's the general procedure? So that's what I'd like to describe for the remaining 5 minutes. So the theorem is that so I'll just say every faithful representation of group G, which is countable and locally subexponential growth. So in group theory, you know, whenever you put locally, that means some property is true for every finitely generate subgroup. So if every finitely generate subgroup is subexponential growth and countable growth, and this embeds into homeo of I, so it can be blown up to a C1 action. And of course, the image, the group itself will not change because you're blowing up, so you're not killing anything. So the resulting representation will be still faithful representation of G by C1 on the interval. And this is given by some careful assignments of lengths to each element. So you pick an orbit, countable orbit on the interval, and you blow up each orbit. And then you put some standard transition function, and it gives you C1 action. So what is the rule for the length assignment? So we at first give a very technical assignment to infinite direct sum of Z using like some trigonometric inequalities and so forth. But after all, we realized that it's quite general, actually. So lemma is that the following are equivalent. That G is countable and locally subexponential growth for every G action on a countable set. Well, 1 and 2 are relatively easy to see. Countable set X. And for every action, every orbit is subexponential growth. Every orbit is subexponential growth. That means for all finite set in G, you count the number of elements in the orbit. And this goes to 1. So that's the meaning of subexponential growth of orbits. And then number 3 is the length assignment. So the length assignment is that, so there exists, what's the quantifiers? So we can just give a number. some length assignment to positive real numbers, because this will be non-degenerate, correspond to lengths of non-degenerate intervals. And this is bounded, actually L1. The sum will be compact interval. So there is a positive real number valued L1 function on G, such that so nu will play the role of the lengths of the blown up intervals. Where did I draw the blown up intervals? So you blown up length of blown up intervals, and it holds for the circle action too. So blown interval such that, so if the group goes to infinity, so that means whenever you consider a sequence element exiting finite subsets, the ratio will be 1 for all S. So if you, right, so because this ratio will play the role of kind of S prime in this length assignment. And whenever, so G goes to infinity, so that means whatever finite so whatever epsilon you consider, there's some big finite subset, bad finite subset. So outside that bad finite subset, this is almost true. So that's the limit of G goes to infinity. And actually, yeah, it was quite surprising to me to see that they are all equivalent. So whenever you have a local sub-exponential growth group, you can have this length assignment. And this new function, it gives us just immediate answer to our blowing up. And then, so really, nothing under the sun is new. So Nicolas Monod emailed us that something very similar was known before. So it is 1950, Jenkins, that, so actually he considered topological group, but in countable setting, what he proved is something very similar. So G is countable, LSEC, if and only if something very similar is true. And it will be logically equivalent because everything is logically equivalent anyway. So whatever epsilon you consider, whatever finite subset you consider. So now in this case, in Jenkins' case, nu is quantified. So given epsilon s, there exists nu. And R such that it is positive valued on the subgroup generated by S, and the value is very similar. So, and such that nu of SG over nu of G minus 1 is almost 1 for all S in S, G in the group. So yeah, this is certainly logically equivalent, although this is not exact the form that we want, because we want nu not quantified by anything. So I'll stop here. Thank you very much.
Thank you very much. Are there questions?
So the work that you had about embedding the mapping class group inside. So is it the case that you use Ivanov conjecture as a motivation for knowing what is true in your case, or is there any statement for embedding? If there's a particular thing you can embed, then you can disprove Ivanov conjecture.
Right, precisely. So if you can embed it into C1 diffeomorphism group of the circle, some finite index subgroup, then it will disprove Ivanov conjecture.
But you have to pick a particular edge, right? Because for a lot of them, you know B1 is 0.
Right. So you just need one. If you happen to find some H finite index subgroup, which is C1 smoothable, then in the interval it is certain stability, but for the circle you can do the same thing. You can find the surjection onto Z after some trick due to Parwani. So so you can disprove Ivanov conjecture if you find the C1 action. And also it's related to property T it is kind of roughly related to property T, because this, I guess we don't know whether this mapping class group has property T, I guess. And also, does there exist any even circularly orderable property T group, countable? So yeah, those kind of things are all intertwined.
Thank you.
Okay, sorry. In the lemma, in the point 3, I don't understand how the point 3 has to do with how to interpret this with a subexponential growth, like algebraic or dynamically. How can we interpret?
Yeah, thank you. So it is not completely trivial implication, but people in the business will just immediately recognize how it gives. So basically, what you want to do is now we have G. Suppose G is embedded into I, say dense subset. So imagine that G is just infinite direct sum of Z. So you can easily embed into I, even densely. So you have your action, say rho, on the interval. And you have the orbit, say G1x, G2x. X is just arbitrary chosen G3x and so forth. And then you blow up the length of nu of G2, nu of G1, nu of G3, and so forth. And because it is L1 function, you still get some bigger compact interval. And then because it's dense, these open intervals will comprise complement of Cantor set. And then, right, there's a natural action, right? So you can say, here, if you see a new GG3, then G will act this way. And then now you specify, so you specify that the endpoints go to the endpoints of the interval corresponding to nu times nu of GG3, but you have to specify which map you will use in the interior. And that is chosen as some nice equivariant map called the Yoko's family, which has derivative 1 at the endpoints. So essentially, for the Cantor set, the derivatives will be all 1. So then the regularity check boils down to checking the regularity at the Cantor set point, which is not the boundary point of the interval. But that is supposed to be 1 by this limit condition. Yep, so this kind of idea was used many times.
Any other question? If not, let's thank the speaker again.